Hi, my name is Matt Gebhardt. I'm a graduate student at the University of Connecticut, working with Danielle. The title of this talk is really the second of the two projects I'll be talking about today, but they're both pretty related, and they talk about sort of diving into the CAMELS simulations and seeing how matter is being redistributed through feedback processes. So I won't go into too much of the background. I'm sure we're all painfully aware of that. To track the most cosmological information from our newest surveys, we need some robust models for the small-scale baryonic processes like supernovae and AGN feedback, especially if we want to use weak lensing surveys that can map the total matter distribution. We need to know both how gas gets moved around by feedback, but also a bit more subtly how the dark matter moves as well. So the plan is to use CAMELS. And so in a paper earlier this year, we looked in depth at how baryons are spread around through feedback. So this was mentioned before in Daisuke and Isa's talks about how we can track particles and see how baryons are spreading. We also, in this second project, want to look at how the dark matter is affected. So it's not directly moved around by feedback, but because relative to an n-body simulation, the gas moves, changes the gravitational potential. And so the distribution will be a bit different. This is important for a number of reasons that have been mentioned kind of all day today. Dark matter detection experiments, core cusp issues, modeling the matter power spectrum. And so CAMELS is a great tool to at least see how, when we include baryons in their associated physics, what can happen to the distribution. And also just vary all the parameters, different hydro codes, and just see what happens. So the first project, as I mentioned, is about how baryons are spreading around. CAMELS people have seen this slide a few times now. It's a pretty simple particle tracking algorithm. So for each particle in the simulation, we find in the initial conditions, its nearest dark matter neighbor particle, and then we just see how far apart they are from each other in redshift 0 for this analysis. And so this isn't necessarily how far particles traveled in an absolute sense throughout the simulation, but rather how far it's traveled from its initial neighboring distribution. This GIF in the bottom right here is not a time evolution, but rather in each frame is plotting gas particles that have spread further and further. So the first frame would be the 10% of particles that have spread the least. They're deep inside halos and filaments. And the last frame is the 10% of particles that have spread the most, which are blown out from the halos and filaments. So as an example of what this would look like in our simulations when we compile the data, we can make a cumulative mass fraction here. I'll use this. So basically, to understand this kind of plot, we're basically just summing up the mass of particles as we look at particles that have spread progressively further. So each of the solid lines here are a different SIMBA simulation where we're changing the AGN jet speed in each of these runs. The green one is the fiducial run. The dashed line here is just the dark matter distribution in the fiducial SIMBA run. So right off the bat, we can see that gas naturally is spreading a lot further than dark matter does. Dark matter only can really spread around gravitationally, whereas the gas feels the feedback. Also, not too surprisingly, if we increase the AGN jet speeds, more gas is spreading further. If we decrease it, it's not spreading as much, which is not too crazy. We can get some numbers off this plot by seeing where these lines would cross different y values. So for example, at say 80% of the mass, we can see where this would intersect in the fiducial run. And we could read off that about 80% of the gas is spreading less than this distance, meaning 20% is spreading farther. And it's 20% of the gas mass spreading farther than 1.8 megaparsecs, which is quite far. SIMBA has some pretty strong jet feedback, as we've talked about a lot this week. We can also read off some values for the other lines for completeness. So of course, dark matter is spreading a lot less. And we can see how changing AGN feedback, for example, increases the spreading of gas a lot. The shaded region here is for the CV set. So just changing initial conditions, which does show a pretty appreciable change just by changing initial conditions in the relatively small CAMELS boxes. So the second part of that project was shown earlier by Daisuke. And so the idea here was that we think that this baryonic spread metric should probably be a pretty good way to capture the suppression of the matter power spectrum. So for each of these simulation pairs, we color-coded each line by the spreading of gas in the hydrodynamic simulation. And when we do that, Daisuke kind of spoiled this a little bit, but we get something like this, which is pretty encouraging. So there's a pretty clear, at least by my eye, correlation between how far gas is spreading in the simulation, regardless of what the actual simulation parameters are, with how much the matter is suppressed. So of course, the downside to this quantity is that it's purely theoretical. It can only be calculated in the simulation. But as we saw earlier this week, ESA has done some great work that's connecting it to actual observable FRBs, which is very promising work. The second project I want to talk about in my 2 minutes and 45 seconds is the sort of back reaction of dark matter. So as we've seen, gas can get spread pretty far. When the distribution changes, the dark matter will follow it a little bit. So this project, we wanted to look at first, like global halo properties, how do the masses changes, for example, and then look at halo profiles, so the density profiles, mass profiles, and then zoom all the way out to the level of the dark matter power spectrum. And then also vary parameters of all kinds, but I won't be able to get to that today, so I'll just show the fiducial models for each. For this analysis, we match halos. We want to look halo by halo and see how they change. So we wrote some code to do this and generated some catalogs for almost all of the CAMELS runs. So if you're wanting to do any analysis like this, let me know. I've been meaning to write a tutorial on how to use this for a long time, and maybe it will get me to finally do it. So looking at the halo masses, we can compute the ratio of the hydrodynamic to the n-body halo masses as a function of the n-body halo in the pair. And so for a few different redshifts here, generally speaking, in Simba and TNG, the feedback is strong enough to reduce the halo masses relative to n-body. In Astrid, not as much is going on. I'm not super trustworthy of these lower mass halos and CAMELS. And then Eagle has some pretty interesting results where at redshift 0, at least, a lot of the masses are increased, which was a bit surprising. Surprising enough for me to want to look at other redshifts to see if anything else was happening. And indeed, at earlier times, at these dashed and dotted lines, we're actually seeing the masses were reduced, but now something has happened since then. So there's both a clear model dependence, but also seems to be a time dependence for this effect as well. We can also look at density profiles, so there's a lot going on here. But each color is one of the different simulation suites. So like the previous plot, I didn't mention this, but it was for the full CV set, just compiling as much data as we can with the fiducial parameters. And so we can plot the density profiles, and here we're scaling by R squared just to make the lines separate a bit more. In the top panel, in the bottom panel, plotting the fractional difference between the hydrodynamic and n-body profile. Solid lines are the total matter profile, dashed lines are the dark matter profile, which we are scaling to match the same mass as we would for dark matter particles in the n-body simulation, because when we include baryons, we have to reduce the mass a bit. So to make a fair comparison, we scale them up. Not surprisingly, perhaps, we do see a lot of increase, a pretty crazy increase in Simba at the centers of halos, and then a reduction in the densities a bit further out as feedback is ejecting matter. In the centers, we have radiative cooling, formation of stars and galaxies. The dark matter follows it pretty closely, it looks like. This is for pretty low mass halos. We can also look at higher masses and see what happens. And converge is a strong word, but the models do get a bit closer as we get to higher masses, presumably because of the higher gravitational potential, sort of muting the effect of feedback. Lastly, as I run out of time, we can look at the dark matter power spectrum. So kind of similar plot as before, now plotting the ratio of just the dark matter power spectrum. And we do still see some pretty significant variations in just the fiducial models. Colored stuff here is the CV set, and the gray region is the full LH set. So that's varying all our parameters to see like kind of the full range these models can provide us. Strongest effect in Simba, as always, weakest in Astrid, it would seem, except when we vary all the parameters, it's a pretty wide range, and more intermediate effects in TNG and Eagle. So I will leave it there and take any questions.
Thank you very much. All right, we have time maybe for one question, maybe two.
Great talk. Quick question to the power spectra you showed at the end.
Yeah.
For the TNG and Astrid, it looks like the power spectra goes a bit up before it goes down.
Yeah.
Do you have an explanation for that?
I definitely have thought about this before, and I'm kind of blanking on the answer I usually give for this. I guess it's just because so clearly it's allowing more clustering of matter. I guess because radiative cooling can increase the density in the center of halos, although I guess we saw in asteroid it's not a super strong effect. But the feedback does seem to be relatively weak. But yeah, especially if we vary parameters, this can go way above, which is pretty wild, which is usually with the AGN parameters, I think in particular. So it's probably something to do with the AGN, but I'm not 100% sure. Maybe there's some asteroid people here that would know better than me.
All right, we are down to 0 seconds. So let's thank Matt again. Thank you.
Yeah, I'll slightly change the title. Okay, great. Hello, everyone. My name is Weiguang. It's a great workshop and seeing friends and catch up very interesting talks and progress in different projects. I'm going to talk about the precisely mapping cluster mass and mimicking the observational signals. And this is mostly done by the two students present here with the account number. You can look into details about the paper. So let's start with something. No, why is I'm sorry. This is green button doesn't go forward. Oh no, yes. Okay, thanks. So let's start with something you already know, but I would like to present to you in a different view. What we see the universe, it's on the left-hand side, right? You see stars, you see gas, you see whatever can emit photons. But what we really want to know is the central picture, right? This gives us what the universe composed mostly, let's say. So with that, you will know, you can do better things, cosmology, large-scale structure formation, galaxy formation, everything that you will get better, right? But what we're really doing is starting from 0-dimension quantity is the halo mass, because we don't know it, and we have to measure it based on different methods. And this is just an incomplete list of the traditional ones. Unfortunately, we have right now the machine learning ones, which is give us much better, and you can combine different multi-wave observations to give you a very accurate. You can check about the papers on very accurate mass estimation of the halos. So that is 1D. Oh, I would like to. You probably don't see the bottom part that I would like to also propose that you see the different methods and also for machine learning that if we can hold a machine learning mass comparison project to estimate the halo mass, that will be great. I'm fully support for that. Though that is 0D and you removed a lot of information, right? And you want to get to know more, and you can go to 1D, which is the halo profile. And there again, that you use the traditional method, but it's getting very hard, right? You have to measure it at each radii. And there's some new methods proposing, but with machine learning, it's as easy as estimating the 0D mass of the halo, right? But on this give us more that you have the profile, you can fit the profile, you know the density profile, you know the concentration, you will estimate the sampling bias, and it's give you a lot more information. But go to even further on to 2D maps, and I think only the lensing, to my knowledge, and machine learning can do that. But why we want them to do that? And you heard about Paul talking about a lot of crises in small structures. I would say that if we want to measure on all those, if we want to spot any difference or contribution to contradicting to lambda CDL model, this is one example that you have to look into detail and look into more details and precisely. And this is a paper by Matthew Mikhail tell us, oh, through the lensing that we found something very serious, that the lensing signal is much higher compared to what we expect, and the circular velocity is also very different. And they introduced a lot of discussion about that. That is come to my point is that we can do this and measure the maps of the dark matter halos. This is an example that we do the theoretical effect, and you're looking at the different observations from IZ to stars, and with the ground truth of the dark matter density maps at here, and you very simply, this is unite map and diffusion model that you can see the residuals, and when you do the combination, there is almost zero residuals, right? So I skip that. This you already very know about that, and this is a little bit of detail that tell you that this method can give you very current measurement. This is a BELS as functional radii, and you can look into the power spectrum and pay attention to note that this is a full image and this is a small scale. And you will notice that, okay, the gas don't allow you to capture the small scale information, right? But the stars, yes. And combine them, you get better result. And similarly, this is MMD, but on the other way is we know the simulation is the dark matter, and we want to see how those baryons look like, so we can compare to observations. We can populate many different dark matter halo, dark matter simulations, etc. And this is another work. It's just the reversing to use the unit to make the predictions. And this is, you're seeing that this is the dark matter map, and the two, probably you cannot see any difference, the true X-ray and that map compared to the predict one. Okay, though that is a verification that we have two models, but it's not as many as CAMELS yet. But this is showing you the YM relation and the X-ray luminosity and M relation. And this is a training set. Everything is looks fantastic. But what we really want to know is, what we want to do is applying this model to the dark matter only simulation. This is a test, and you're training on gizmo and apply the dark matter to get the gizmo result. And training on gadget X, and you will get gadget X result. But if you do the command, you can train them together, right? And you will find that this one, the green one, is actually predicting the result from the gadget X result. So why that? Have a look at the paper, and we have a detailed investigation on why that. Okay. So I have just 1 minute. I would like to leave the conclusions here and give you a little bit advertisement. And the first is the REST journal, that if you're doing machine learning stuff and new techniques and applications, and this is where this journal is dedicating to. And another little tool I played around and developed, and if you feel useful, and try to look into it. Okay, assume that I have 20 seconds for a question. Great.
More than
Thank
that.
You.
Thank you. Thanks.
Oh, that's, I okay. More, I should say more things. And the I skipped a lot of details. Should I start from earlier again? Okay. Anyway, and I would like to just let you know that all detail, the demo is in details, right? And ask me about the demos.
Thank you.
So yeah, I think you went a little bit fast here, but so you have some kind of robustness, right? You train on one and you test on the other.
Yeah.
So what I understood is that you said that this works or this doesn't work.
oh, it's work. It's just that you would expect, right? The result. I hear, oh, sorry, I'm confusing. Here, this is, oh no, this is just the prediction, sorry. This is the command. We don't do exactly that it's applying gizmo to gadget X or the other way around, because this can still work. We test that, it still work. It's just predicting the same as you trained. There's nothing fancy there. But the real universe, think about, we are just doing simulations. The real universe is just something in between, luckily, if we are lucky, and something in between those simulations. So that's why we try the combined version. Hopefully that is somehow that the common feature will show up and give us something that we expect in the real universe, right? So that is the idea why we do the combined version. But the thing is that the combined version have some preference. It's not something lying in between. I hear it's more or less lying in between. But if you go to the real predicting power, this is more low mass halos. But the real predicting power is in the cluster mass, right? But it's preferring some of the simulation. So that is the weird thing we found.
Okay, very good. We are down to 0.
Okay.
But yeah, let's thank Weiguang very much
Thank
again. Thanks, great talk. And our next speaker is Xavier Sims, who is going to tell us about the impact of large-scale environment on galaxy evolution in CAMELS.
Hello, everybody. My name is Xavier Sims, and like Danielle just said, I'm going to be talking about the impact of large-scale environments using CAMELS. I'm also a 4th-year graduate student at the University of Connecticut, if I didn't mention that already. So to begin with, I'd like to make it clear that when I'm talking about environment throughout this talk, what I'm really talking about is whether or not a galaxy is forming in isolation versus in a more dense region of other galaxies, such as a cluster. There are a lot of equivalent definitions of environment that people use, including number densities. This surface density here is an example of a number density used to define an environment. I won't go through all the details, but understand that this is a number density, and the larger the number is, the closer the neighbors are in proximity with each other. And this is an observation paper from 2003 by Gomez. And here you see that star formation rate actually decreases as neighbors are more close together. We can take this a step further using simulations because we have the ability to look into certain properties that are notoriously hard for observers to measure, such as dark matter halo mass. An additional advantage that we have using CAMELS specifically is that we're able to compare results from multiple feedback implementations. So this is a map that I've made as a visual representation of how environment affects galaxy evolution in SIMBA. So what you're seeing is a dark matter density plot with galaxies overlaid. The circles are halos. The smaller markers in the middle of the circles are satellites, and they're all color-coded by specific star formation rate. So blue means actively star forming. Red, very red galaxies are quenched. You see that the most massive galaxies are always in the most dense regions. And if you look at void regions, you see a lot of smaller, more actively star-forming galaxies. We can expand this to 4 different galaxy formation models. So I'm using SIMBA, Iglesias TNG, Astrid, and Swift Eagle for my work here. You see immediately certain similarities and certain differences across the 4 simulation models. One similarity that they all share is that the most massive galaxies always appear in the most dense regions. A very big difference is that while in SIMBA you see a lot of very actively star-forming galaxies in the void regions, in Astrid and Eagle on the bottom, in the void regions you see a lot of small quenched galaxies, indicating that Astrid and Eagle are very good at suppressing star formation rate with stellar feedback. So the question is, how do we quantify environment so that we can really analyze its impact? And what we are using is a quantity called galaxy overdensity. To briefly explain, it's another number density using 10 of the nearest neighbors to the galaxy. What we do is we take the distance between any reference galaxy and its 10th nearest neighbor. That distance is the radius of a spherical volume encompassing all 10 neighbors. The number of neighbors divided by that spherical volume is galaxy density. Galaxy overdensity is that quantity galaxy density normalized by the average galaxy density of the entire simulation volume. And then to analyze impact of environment, we've pinned down 4 galaxy and halo properties to use. The halo properties are halo baryon fraction and halo CGM fraction, or circumgalactic medium fraction. Just adding up the baryons divided by the halo mass and the mass of CGM gas divided by halo mass respectively. And then our galaxy properties are galaxy star formation rate and galaxy gas fraction. And galaxy gas fraction here is defined as mass of gas within the half stellar mass radius divided by the mass of gas plus stars within the half stellar mass radius. So the very clear correlation between galaxy overdensity and halo mass, which I alluded to earlier, does present an issue, but we've created a pretty good workaround. So instead of comparing galaxies with different overdensities full stop, we divide them into different mass bins first. Like this one. Each mass bin is a width of 0.25 dex. Within each mass bin, a galaxy may be divided into one of 2 camps. If the galaxy's overdensity is less than the 25th percentile of the mass bin, it is underdense, it's given this blue color. If it is above the 75th percentile of overdensity, it is classified as overdense and given the red color. The blue and red are the median baryon fraction values for underdense and overdense galaxies respectively, while black is median of everything. And to account for error, we have included the shaded regions which represent the 25th to 75th percentiles of baryon fraction for either camp. And here, so once again, this is SIMBA, baryon fraction versus halo mass. We see the strongest trend with low mass halos. It indicates that when a low mass halo is left alone, far away from other galaxies, it is far more efficient at holding onto its baryons than if it were close to more massive galaxies exerting feedback, among other things. Expanding this to all 4 galaxy formation models, we see some pretty significant differences. In TNG and Astrid, we see the strongest trends with high mass halos. With Eagle, we see a trend everywhere, but it is the opposite extreme. And this is, the interpretation for this is that because stellar feedback is so efficient at suppressing star formation in Eagle and blowing things away, it's better to be in a more dense region where the more powerful potential well is going to help you hold on to those baryons. Looking at CGM fraction, we see systematic trends that are identical to that of baryon fraction. And then moving on to the galaxy properties, starting with star formation rate, we did this a bit differently. So here we have 2 rows of plots. The top row is central galaxies, where you see very weak trends, if any at all. However, when we isolate satellites in the bottom row, we see very strong trends across all mass bins. And what's interesting is, unlike the previous 2 slides, we see results that are very consistent across every galaxy formation model. We see that underdense galaxies have higher star formation rates within every mass bin relative to overdense galaxies. Gas fraction, once again, we see very consistent results across every galaxy formation model, with blue being over red in every mass bin as long as we're isolating satellites. And once again, trends are very weak when isolating centrals. Okay, less than a minute to plug. So I also have something that I wanted to advertise. So I have a few exciting things in the pipeline. One, so we're on the tail end of writing paper based on the results that I have just showed. The second paper is going to be looking into how parameter changes using the 1P and the L8 sets affect the trends that I've identified already. And I'm also looking into making an eventually publicly available data set that includes different measures of environments and galaxy properties. And if anybody had the chance to see Jonathan Mercedes Feliz's poster yesterday, using dispersed to identify cosmic web filaments in CAMELS, I will also be having definitions of environment using the cosmic web filaments, such as distance to nearest neighbor filament and similar things. 7 seconds left. So thank you all for listening. And I'm happy to take any questions.
Okay, thank you very much. Very good. We have time for questions. In the back, Ana Maria.
Excellent talk, Xavier.
Thank you.
You touched on this, and I'm sorry, I was busy reading the slide. And when you were in your baryon fraction plots comparing the 4 simulations, and you touched that Eagle has a different trend, not only in the halo mass bins, but overall there's like a completely different trend, because there's this bump in Simba, TNG, and Astrid, like around 10 to the 12 solar masses that doesn't exist in Eagle. Can you say something to that?
Yes. So yeah, I didn't touch on this. Very thankful for the time that I was given, but not quite enough to go over every detail of every plot. So once again, this is down to stellar feedback being so powerful in Eagle. So the reason that you see this increase in Simba, TNG, and Astrid is because what's happening is as the halos get more massive, the potential well is effectively overpowering the stellar feedback, allowing more baryons to coalesce. However, in Eagle, stellar feedback is so powerful that it suppresses even that as the halo gets more massive, the potential wells are still not powerful enough to overcome the stellar feedback. Baryon fraction remains fairly low. It's a pretty flat, slight increase until you get to about Milky Way size. Very good question.
All right, so we have 10 questions for a really quick question.
A softball one would work.
All right, let's thank Xavier again. Thank you. And our next speaker is Patricia Iglesias Navarro, who is going to tell us about pixel-based fitting of stellar populations.
Yeah, I hope this works. So I'm not working with CAMELS, but well, I'm Patricia. I'm a PhD student at the Instituto Astrofísico de Canarias, working under the supervision of Mar Huertas and also Johan Nappen. And today I will tell you about how we can infer the population properties from result photometry with simulation-based inference. So the idea is to measure the population properties of galaxies combining both high spatial resolution with multi-band photometry. If we have good enough data, we can move from integrated density fitting to result density fitting. And thanks to the capabilities of grid telescopes such as the James Webb Space Telescope, we can get very high resolution images of galaxies, even at galaxies at redshift around the cosmic node, such as this. However, even when we have good data, density fitting tools haven't really improved so much. Either they are based on chi-square minimization, and they don't really help us with degeneracies because they don't provide uncertainties, or they are based on the Bayesian inference, but they are just too slow. Just to give you some numbers, it takes from 10 to 100 CPU hours to analyze one single galaxy with this method. And with James Webb, we can analyze, we can observe up to 25,000 galaxies in just 2 days. That will mean that for analyzing 2 days of observations, we need from 10,000 to 100,000 CPU days. That is not, of course, non-feasible at all. And this situation even gets worse when we move to LSST or Euclid surveys. So our approach is to use, as I say, simulation-based inference. So we're gonna simulate synthetic data in a forward model, then feed like real observations and compare against the truth. Which kind of physical properties I'm talking about? Well, stellar masses, star formation rate, ages, metallicity, and dust attenuation. The forward modeling will be done using star population synthesis code. This is our simulation here. These observations are going to be photometry, in particular 19 filters of HST and JWST, both medium band and wide band filters. And we're also complementing this information when available with spectroscopic redshift, because we find that by including this information, we can constrain much better these properties. And how we are going to solve the inverse problem, we are going to use normalizing flows to get posterior distribution of the properties. So yeah, I think I don't want to get into a lot of details here because this has been already explained during these days. But basically, what we're going to do is try to obtain non-parametric forms for the posterior distributions by starting from a very simple distribution, Gaussian, for example, on the left, and then applying invertible and differentiable transformations that are going to help us to reach there. And the good thing about this is that the functions are learned in the training. So once the training is completed, it's very fast to obtain posterior distributions for new observations. That is what we say. This method is amortized as opposed to, for example, MCMC. And this is going to help us to accelerate a lot the Bayesian inference. So yeah, going back to where we were before, our input are going to be observations, 19 magnitudes and their errors with spectroscopic redshift, not necessarily from JWST. It can come from ground-based surveys. Yeah, we are also trying to add some realism here. So we are adding noise that comes from the real survey. And also we are trying to mimic the depth limits of the survey. So we can like characterize non-detections, like for example, HST dark galaxies. And we also can allow the number of filters to vary if needed. And the output are going to be posteriors of the physical properties. As you say, not necessarily Gaussian. Yeah. But we need to be sure that the posteriors are well computed. We have performed several tests as well as like comparing with MCMC posteriors or doing simulation-based calibration. But here I wanted to show something I find a bit more qualitative and easy to understand. Like according to the Bayes theorem, if there is no information in our observations, we should recover the prior. The posterior should be like the prior. So yeah, that's exactly what I'm taking into account here. In the y-axis, I have the width of the posterior with respect to the width of the prior for several properties that are each of them color-coded with different colors. And this is done for 1,000 galaxies in the Hubble ultra deep field and all the pixels within that galaxies. So basically what we see is that if we plot here the mean signal to noise in these filters, as we move to very low signal to noise, we get this value exploding. So we are basically covering the prior when we have no information, where we are just dominated by noise. So here we can do some cut, like for example here, at signal to noise equal to 10. It of course depends of what you want to do. And then you can put some thresholds on the pixels you're gonna try to fit. Yeah, and on the right, I'm showing exactly that threshold, signal to noise equal to 10, but like in the physical properties plane. In the y-axis, we have the total stellar mass of the galaxy. On the x-axis, we have the spectroscopic redshift. And what I'm showing is the fraction of pixels in each galaxy that we can fit. And we see that we have enough pixels with that signal to noise, even at redshift 5, at a solar mass 10 to the 8. So we really can fit a wide range of galaxies in this way. Yeah. So yeah, I'm just showing here this galaxy. This is the galaxy I'm gonna fit today, even when we can do that for 1,000 of them. It has 5.5 pixels that can be fit in less than 3 minutes with a single CPU in my personal laptop by getting 500 samples of the posteriors per pixel. That is 4 orders of magnitude, 3 to 4 orders of magnitude faster than classical Bayesian approaches. Yeah, let's go to see the fits. Yeah, so before that, I just wanted to show here how this galaxy looks like in a single filter. in the RDS medium band filter from NIRCam. And also, like what we have, the dark circle there is the PSF size for that filter. So basically, we shouldn't expect like variations in the physical properties below that size. And yeah, like here, I'm just showing the maps of the physical properties as the means of the posterior Wargating, because remember, we have posterior for each of the pixels. Yeah, basically, I'm retrieving something that is, I think, very like easy to understand. We just have most mass in the center than in the outskirts. But then when we look, for example, to the star formation rate per pixel, we see that the star formation rate is mainly located on the disk, but also in this cloud, like blue cloud over there, which also makes sense. It looks bluer in this image. Then we can analyze, for example, the age of the first stars. Again, we get older center, and then we always see this cloud over there that looks younger. And also the age of the last star. Same trends, be different in the outskirts. About the metallicity, we get a center that is more metal rich than the outskirts. Yeah, and the same with the dust attenuation. This is very interesting because we have a very dust attenuated center, while in the clamp we have almost no dust attenuation. Yeah, and don't forget that we have uncertainties for each pixel. So with this, we can do a lot of things. I'm just starting to try to look for scientific cases. Right now, I think we're focusing on stellar mass gradients, trying to trace the structure evolution across different redshifts, but we can focus on many other things, like for example, star formation clamps, but also dust distribution, mergers, and even look for very low metallicity regions. All of these per pixel for thousands of galaxies and up to redshift. Yeah. So I will finish with my summary slide. Yeah, thank you.
We have time for one question.
So super nice work. So basically what you were showing were the mean of the posteriors, I guess. So what happens if you take like a random realization? Will you see like a small structure in these images?
Like you mean a random sample of the posteriors?
Yes.
Yeah, I think it really depends. The most probable thing is that you will see a very similar thing, a similar thing to the mean, but it of course can happen that some pixels are like just weird. It depends. For example, for stellar mass, you usually get narrow things, while for the age of the stars, you get very wide things, mainly resembling the prior. It's important to go to the posterior and analyze, like, are they unimodal, multimodal? Yeah, it's not everything like the mean looks like.
Any last question? Okay.
Is your methodology still prone to the traditional age metallicity degeneracy in these efforts? Yeah.
Yeah, I think that with the, of course, there is always the age metallicity degeneracy, but I don't think that we can actually break that because the width of our posteriors are already like too wide. We are just working with photometry. Yeah, they are just too wide to disentangle this.
Okay. Very great. Let's thank Patricia again. Thank you.
Yes. Hi, thank you. So thanks to the organizers for allowing me to speak at this conference. It's been awesome. I'm David. I'm a 6-year PhD candidate in physics at the University of Michigan. Shameless plug, I'm applying for postdocs right now. And I'm excited to talk to you today about work I've been doing with my advisor, Camille Avestruz, as well as Nick Nedden at the University of Chicago on trying to better understand cooling and heating functions and how they're affected by the incident radiation field with machine learning. And so I want to clarify exactly what I mean by the cooling and heating functions. And so these are really a useful way to describe the thermodynamics of gas clouds in galaxy formation. And so we're going to break up the rate of change of the energy density of one of those gas clouds. It's pretty diffuse, so we only need to worry about the radiative term. And in the heating function, gamma, we're going to put any process that increases the energy density of the gas, so absorbing photons from sources like stars and quasars. And in the negative cooling function, lambda, we're going to put any process that decreases the energy density of the gas cloud. And then because these processes tend to be collisional, we're going to factor out the density squared because that's the density dependence we expect for collisional processes. And so in general, these cooling and heating functions are going to depend on the detailed distribution of energy levels and ionization states of the particles in the gas. And so if we have a gas with solar element abundances and no incident radiation field, so those balances are purely determined by collisions, the cooling curve as a function of temperature looks like this. And these bumps and wiggles are due to the contributions from different elements, and they occur at temperatures that have to do with the ionization thresholds for each element. And so this first peak at a few times 10 to the 4 Kelvin is due to ionization of hydrogen, and the contributions from all the other elements are shown in these thin lines here. And so they look more complicated because these elements have multiple ionization thresholds. And so the main thing I want to point out with this plot is that we know how to calculate these curves. You need a photoionization code like Cloudy that calculates the equilibrium that occurs between collisions and photoionization of all of these ionization states. But that's slow because we have to track these collisions between order of magnitude 100 ionization states that might be relevant. And so if we're trying to run a hydrodynamic simulation of galaxy formation, we really don't want to have to calculate these on the fly at every time step because the gas properties of the gas are going to change. And in addition, as you see here, if we change the pattern of element abundances, the total cooling curve is going to change. And if there's an incident radiation field, that changes the cooling and heating functions from this plot as well. And so in practice, in a simulation, what we really want to do is we want to pre-compute a table of exact calculations and then interpolate between them. So for the case that I'm going to be talking about today, we're going to interpolate the cooling and heating functions at a fixed pattern of element abundances. And as inputs to that interpolation, we have gas properties, the temperature and density, and then we want to characterize the incident radiation field by some averages in frequency or energy. And so we don't need machine learning to do this. We can do this with a linear interpolation table, but machine learning is a really useful approach for two reasons. One, these functions are intrinsically nonlinear. And so when we try to linearly interpolate a nonlinear function, we're always going to get large errors at some points in parameter space, because when we have fixed spacing in our interpolation, we inevitably get those. But machine learning allows us to have adaptive spacing in the way we do the interpolation. And specifically, I'm using the tree-based algorithm XGBoost, which directly allows for this kind of adaptive spacing. And another advantage is that this is a high dimensional problem because there are many different frequency averages of the radiation field that we could consider, and machine learning gives us some nice feature importance and interpretability tools that we can use to study that. And so specifically in work that we released on Archive earlier this year, we specifically looked at interpolating cooling and heating functions using six energy bins to average the radiation field. A specific realization of the radiation field we assume is shown here, and we use 6 energy bins. So the x-axis here is showing the photon energy in Rydbergs. 1 Rydberg is 13.6 eV, the ionization threshold for hydrogen. So we allow our bins to go from just below that threshold all the way up into the X-ray part of the spectrum. We train models using all 6 of these bins, and then we ask what models or what bins are most important to the model predictions. And what we find is that 3 are particularly important. And those happen to be this lowest energy bin below the threshold for ionizing hydrogen. And in the way we set this up, this is the only bin that includes the overall amplitude of the radiation field. So it definitely wasn't surprising that that's important. Another important bin is the bin just above the hydrogen ionization threshold. And this is where the radiation primarily responsible for ionizing hydrogen and neutral helium lives. So again, not surprising it would be important. And then the final bin that the models think is particularly important is our highest energy bin, which is completely dominated by the quasar contribution to the radiation field. And so when I initially computed these feature importances, I was a little skeptical, but there's a test that we can do, which is if we train a new model that just sees these three most important rates, how does it compare to a model that sees all of the bins? And we find that they perform pretty similarly. So what I'm showing here is the frequency of errors on the y-axis of a given size on the x-axis. And so to guide your eye, the performance is better when the curve is lower. So we have fewer errors of a given size, and it's particularly important as we go to the right of this plot and the errors get larger. And so the model that sees all 6 bins is shown in the solid red line, and the model that sees only the 3 bins identified as most important is shown in the dashed red line. And so this is specifically for interpolating the heating function at solar metallicity, but in every case we consider, this looks pretty similar. And so the performance of the 6-bin model is a little bit better, which we should expect. It sees more data, it should perform better, but the performance is really very, very similar. And so what we conclude is that yes, these 3 energy bins are in fact enough to predict cooling and heating accurately. And we tried only selecting the 2 most important bins from the feature importance analysis, and it does not look nearly this good. 2 bins are not enough. And so with a little bit of time that I have left, I want to plug the work that I'm doing now, which hopefully will be up on the archive in the next week or 2 before the end of the year, where we actually plug one of these machine learning models into an isolated galaxy simulation and compare it to the same simulation using an existing interpolation table approach. Our machine learning model is shown in the dashed orange line. The existing interpolation table approach is shown in the blue line. And the shaded regions are showing the spread of the temperature in each density bin. And we find that in general, these look pretty similar, but there's this region from about 10 to the minus 3 to 10 to the minus 1 in the number density where our machine learning model actually predicts a significantly hotter gas. And so I'm excited about this, and I look forward to the paper being up soon. And with that, thank you for your time, and I'm happy to answer any questions.
You. So this feature analysis you did to isolate the 3 bins that are good, did it tell you anything about degeneracy in the other 3 bins that make it suck? Like,
yeah, that's a really good question. So we're using SHAP values to do the importance. So we didn't look directly into the interactions, but we did also spend a lot of time just looking at the correlation between different features. So I said that we only include the overall amplitude in one bin, and we specifically removed that from all the other bins to lower the correlation, but we did look a lot into the correlations between the bins.
Okay.
Talks. I don't know very much about heating or cooling, but so maybe this question doesn't make any sense. But in the end, if you're keeping track of just 3 bins, do you find that like the memory requirements of the simulation go down, or does it end up having a similar memory requirement in the end to do these types of calculations?
Yeah, okay, that's a really good question. So I guess 2 things of, one, I think bigger picture, the memory problems actually come from doing these machine learning models at all versus the interpolation table, because basically lookup tables are super efficient. You can do them super well in Fortran, they're really fast, but the nice thing about these tree-based models is they do not really scale with the number of features. And so in practice, changing the number of features doesn't really change the data size of the trade model.
Thanks.
Okay, one last question, Xavier.
That your ML model is doing better than the interpolation table, or are you saying that it's close enough to the interpolation table that it's okay?
That's a really good question. So I'm not claiming that it's better. I think in this plot, we are trying to claim that it actually is different, at least in this one region of parameter space. So really the whole thing that we're doing here is trying to figure out how much of a difference the increase in accuracy from the machine learning makes in different regions. So if it's an increase in accuracy,
could you, if you increase the number of bins in the interpolation table, would you then expect it to tend towards the ML model? Does that make sense? Like, but because and if you were not interpolating at all, but just evaluating the table on the fly, then that would be the most accurate thing. But you could approximate that better by increasing the number of bins in the table.
Yes, absolutely. And something I very much want to do in the future is try and use the feature importance analysis to build better interpolation tables. Exactly like you were saying.
Okay, very good. Let's thank David again and all of the speakers of this session for the wonderful set of talks. And I think that we are ready for discussion.
Perfect. Now you can hear me. Great. All right. So to keep us a bit awake and motivated, we are very brave. We're going to do this live. Take out your phones, scan the QR code, and start voting. How do we reach accurate galaxy evolution models? I've hidden the responses. I don't want you to get biased. Everything is anonymous. Do not be shy. Yeah. It's up to you to interpret that. That's right. There we go. We have the first brave person. You have a little counter at the bottom. We don't vote. 7. Wow, the number is growing. Excellent. Look at that. Fantastic. We have a few more of those, so you don't need to overthink, okay? The first thing that comes to mind. Very good. Excellent participation rate. How many are we in the room? Should be something like 50, 60, 70? How many? Somewhere there anyway. All right, we won't wait forever. Let's see what the audience has to say. Oh. Of course it doesn't work.
Yes, sure.
My goodness. Do it from here. There we go. It disappeared. Oh, when I press H, it goes into search mode. I don't know what's happening. There we go. Yay! Excellent. All right. So
what do we have here?
I think you're either all tired or very pessimistic. Nobody's happy. Nobody's happy. Okay, fine. More data. I'm interested. Tell me more. Tell me what kind of data. Tell me who wants more data.
And what kind of data? this data naively think is observational data. That is how we constrain the models, right? So that's why I'm voting for this more data. Yeah. Okay.
But what kind of data do you have? You know, you want X-ray, whatever profiles you want.
More data.
More satellites. We heard a lot about satellites. All of the data.
All it. Yeah.
I'm with you.
I'm too greedy.
I'm with you on that. Anyone else wants to volunteer an opinion on any of the list, or maybe something that's not on the list?
Please go ahead. Don't be shy.
Yeah.
I think
Please.
it is interesting that like more theory is not an option.
Well, I put it on the sims. Yes, but more physics, more expressive.
Yeah,
Yes. I hesitated to add that to the list. Yes, we can definitely improve the list.
There will be questions about physics.
Yes, coming. All right, shall we go to the next one then? So in principle, if you're still on the page, then the thing will advance by itself, in principle. In principle. So there you go, data. I'm glad you answered data in the previous one. It is the same page as before. One second.
You can up, yeah, move it up.
There we go.
Here we go.
Ooh, distributions. Interesting. Yeah, go ahead.
No, go. Yeah, interesting that we have a full distribution. It's not like we need something, single thing. We all need.
We need everything.
Need everything, including I don't care. I love that.
It makes me very happy that you want more data. We didn't hear anything about very high redshift stuff though today. Yeah.
It's very interesting that either you really want high redshift or you really don't want high redshift.
Yeah. We heard a lot about the low redshift stuff, right? Like dwarf galaxies and all of the good stuff, Milky Way things. Excellent, but we didn't hear anything yet. Anyway, maybe tomorrow. There is always hope. Fantastic. You don't like the AGN for some reason. All right. All right. Good.
Your favorite AGN is not the top, unfortunately.
What can I do? I need to change job. All right. Now, Lucia, this is for you. Physics, galaxy physics. Tell me your association. Let's make it a sociology or not sociology, a psychology experiment. We are not into the cosmology regime yet. I leave this to the expert later. It looks very dramatic. It's like 6 responses. It's mesmerizing. It's like watching the simulation. We seem to have some winners in the middle anyway, maybe. There you go, satellites have appeared. We converged, let's see. Ooh, important. Very accurate, important. Embarrassing, yes, let's pick some of the interesting ones.
Yes,
faith. Somebody has faith. I'm not sure I do. Goodness, I think we have a full range of emotions here. What is this number?
To the future, maybe.
Maybe that is the answer. All right.
Let's move on.
Probably.
Actually, yeah, maybe somebody wants to say something about this. Impressions.
Embarrassing. Yes.
Should we maybe count like how many positive versus negative?
Yeah, we need to run a sentiment analysis. Absolutely. More feedback. Even more feedback. Fantastic. All right. So
everybody's happy with this picture?
It's embarrassing. Opinions on subgrid physics or galaxy physics in general. What is your wish list? What would you like to see? Dust, we heard today, which is super important. Shall I dare to say the M word? Magnetic fields.
I can say, I'm a cosmologist, right? So I really don't care about this. So I just want to marginalize.
Perfect.
I know it's complicated.
Did you answer? I don't care. But then it doesn't work, does it? Right? If you don't have correct baryon physics.
I think, to do cosmology, I think the goal is really maybe not to really understand. I don't know. As long as you are able to put some kind of error bar, I think that's fine, at least for us. So that's kind of, you only need to know this thing to the point where you can marginalize over.
Are we there? Are you happy with your marginalization?
Yeah, I don't know.
Perfect. So that's why we always had the answer, I don't care, for you.
Well, I think it's probably related to sociological understanding of what science is and what we're looking for, right? Because we can look for some new laws, and some people do that, or we want just to model the universe that we live in, and we'll be happy if our model works. Or maybe we want to learn something that we don't know yet from using those observations and simulations. So for different people, it's probably a different thing, right?
I think even from a cosmologist perspective, I think I'm going to push back on Paco and say that it's important, because the whole point of running simulations like this is so that we can get to smaller scales and extract more cosmological information. But what happens if, let's say, all 5 or 6, I forget how many CAMELS simulations, we want to marginalize over all of them, then perhaps the uncertainties we have to add by that marginalization outweighs any gains we would get by going to higher K, basically. So maybe it is important to nail these down a little bit.
So yeah, I was looking at this for a while, looking for one of my works. And I was looking for a tiny one because I didn't think that nobody was going to be that optimistic. But then I found it. There is galaxy Sugri physics is improving. And it's very nice that at least there was more than one person.
I think it's a good statement.
Don't lie, yes. Daniel. You say bullshit, I'm pretty sure.
It's a little rude. Yes, you want to say something more about the improvements? What is your hope for the next year?
To keep improving.
Okay, that's for the next year. How about next 10 years?
Maybe keep improving while reducing while still like varying parameters for Paco to marginalize over certain.
Yeah, please.
Any takers, Daniel?
I don't know. I understand better the physics. I guess a lot of interest in physics that it's just interesting on its own, even if it's not helpful for cosmologists. But anyway, I think models that are more predictive, less numbers of free parameters. So in principle, the higher the resolution and the more physics that we can model explicitly, hopefully we can reduce the number of parameters, so make models more predictive. But like how what's the what is the end point of this? And I don't think there is an end.
Don't see any more hands. Maybe it's time to go into the dark sector.
No.
All right, so we heard about this today. Small scale tensions and dark matter physics. Answers keep coming in. Ooh. again, I think people want answers.
That's really interesting, and that's actually very encouraging. Because if I would say, if most of the people would say just CDM, well, that would be boring, isn't it? If people would say MOND is the thing, well, it might be interesting by itself, but we don't have compelling reasons to believe that this is true. And of course, I'm really happy that only 2 people don't care.
Which one would you choose?
I would definitely choose the small scale tensions should be found in observations more. I mean, whether they exist, whether they not exist, whether they can be explained with normal physics, or we we'll have a new model of dark matter. Who knows? But definitely observations is something. I mean, physics in general, this is cosmology, but in general, physics is progressing from the experiment, not from a thought. And forgive if somebody likes, say, physics in current day physics in the sense of loop quantum gravity or something like that, string theory. I mean, they are motivated by beauty, which is fine, but they have very little connection to observations or to experiment. And therefore, they're in trouble now because they don't have anything to compare with. On the other hand, all the physics is motivated by understanding what's around us. All the laws of physics were obtained by first observing something, finding misconceptions, finding something that doesn't fit in the picture, right? And I think cosmology is no difference. So I'm for observations too.
Does anyone want to defend their Mond selection? You can, it's not, I'm not picking on you.
Maybe people can comment on why they think CDM is the ultimate dark matter model.
So can I mention? So maybe just to play the devil advocate here. So I mean, as far as I know, for instance, in the old days, I mean, people were looking at the planets, right? And so we know the orbits very well. But as far as I know, there were even like very old models that were able these EPIs, these kind of things, right? So
they actually worked real well.
But it was maybe not the correct interpretation, right? So
it wasn't the correct interpretation, right?
So in that case, with more observation, you will not have probably really, got anything else. I mean,
yeah.
But it was through more observations, no? Eventually, not everything can be explained through the epicycles.
Really? I thought it was just like... I mean, my understanding is that with this, you can really explain the orbits of all the planets. It was really like the change in the, it's like, okay, so is the sun really the center? I don't know, yeah.
Yeah, it's actually very true that if you take the Earth-centered model with the epicycles and just take those epicycles, which were done actually very accurately, and then simply convert this reference frame into the frame of the sun, then yes, epicycles immediately become ellipses.
I think we also have the opposite example that if Kepler had higher accuracy data, he wouldn't be able to have his laws, right? That is another problem.
Yeah, let's move.
Stakes are getting higher.
Is it blocking the first answer? Oh, it doesn't matter. They have. Okay.
Ooh.
Dark matter doesn't exist 5%. And interestingly, everybody cares.
Even Paco. Oh, no! Doesn't count.
Okay, can anyone tell why direct detection is gonna win? I can tell you my perspective in principle, if you will. See, we started with WIMPs, and we thought that we're gonna find them because of the WIMP miracle. We know that the cross section is gonna be something like 10 minus 35, minus 37. Now we're down to minus 10 to minus 46. Still nothing. Last summer, in June, I guess it's June, there was a report from Xavier and NT that they actually see the neutrino fog from solar neutrinos. So they hit the floor there. Neutrinos now can be seen in direct detection experiments, but not the primary particle we're still looking for. Maybe it's not just there. Maybe it's a wrong place, wrong parameter space that we're looking for with direct detections. Let me remind you that cosmology, well, not cosmology in this case, but astrophysics in general actually helped us understand that we have neutrino masses. The first experiment, the chlorine experiment by Davis, and then Galaxy and SAGE, and then SNO. We actually know that neutrinos have masses from those experiments, not from CAMELS, which was way later. So there is an example where we can actually use astrophysical data to constrain certain, or even understand what the properties of the particles are. Any thoughts?
I feel like I have small gestures. I'm a bit of a narcissist, but even though I feel like only that provides us with many modes of evidence, like this is the only way we can have a few, maybe it's a naive view, but I think it's the only way we can have a few, not observations, but like evidence pieces to the puzzle. And detection is just like one set of parameters that we kind of have to fit in. Hope so. I think.
Okay, thank you. Anybody else?
Maybe they will not detect the particle because it's all primordial black holes.
If they're primordial black holes, why haven't they evaporated by now?
To evaporate.
Oh, you mean 10 to the 17 grams, something like that?
Sure, yeah, something like that, asteroids.
That's a where's tiny window though?
Well, you know, maybe we messed up the experiment and the window is bigger, you know? Maybe the cap was on when the micro lens showed up, I don't know.
Okay, fair enough. Let me remind you, by the way, that gravitational waves were first discovered in the double pulsar experiment. I mean, the observation that the period of the pulsar has been changing over 20 years. And that was a Nobel Prize, actually. So LIGO is the second. So maybe astro. I'm actually here for the astro, not the direct detection, especially because we still have nothing, despite all the searches. Colliders, why do you think colliders? We will unlikely have anything bigger than LHC. And so far, they don't have anything. High luminosity LHC. Okay. So you've been in that part. Okay.
The particle people are not as enthusiastic though. So I don't know.
Well, if the 22% are correct, so what shall we do? I mean, the dark matter particle will never be detected. Does it mean it doesn't exist? Yes.
They'll have to keep paying us to look for it for a long time.
Oh. Okay.
I think they fall in the 2% category.
Yeah, let's move. Anything that's not CDM, anything that has certain properties, SIDM, endothermic, anything else.
That's not in the box.
Exactly, that's not in the box.
Cannot keep voting after I've shown the results. Come on.
It's okay. It's not a big issue. I don't have any comments on this. I think we're all happy with our optimism and desire to investigate. Because no is actually a very pessimistic thing. So
Somebody care to comment?
okay. You think it will completely kill the? Okay. No, degeneracy is a big problem. But hopefully with better resolution.
I was just gonna say I voted for no alternative DM domain is too big. I did like Chang's point the other day, which is that lambda CDM, no one has proved it wrong yet. And if you're like allocating resources to like what things you should simulate until something else is convincing, maybe we stick with lambda CDM for the most part and just allow people, to slowly trickle into other domains. But that's not a strong opinion. That's just a feeling.
How would you reply to a reminder that we have small scale tensions?
Yeah. Well, I don't know. I don't know. I mean, it doesn't. I have yet to see from my limited experience if DM can solve that. Alternative DM can solve that. Yeah. Or there is like, a strong preference for one DM because of the small scale tension.
more thoughts, more comments?
I think a lot of the people agree with your view, in fact, even though they voted here, right? This is not, it does not depict what people actually do, from my limited understanding.
Interesting for me is that the first and the last are nearly equal in the number of responses. I actually thought that the last is gonna be the dominant one.
It's probably where we're heading towards, yeah. It's the easier.
I would just add that we want to think out of the box all the time about everything. Be optimistic.
Yes, I think we should interpret this as optimism rather than the plan for the next year or 5 years or 10 years.
Can I actually ask, maybe somebody can tell me, when we talk about baryonic effects, here we're talking about modeling them, but in reality, are we missing something physical, or are we missing something in terms of, I don't know, some simplifications because of the simplifications that we use for our subgrid models? Any strong opinions on that? Or it can be both?
Probably both, right? Probably.
Okay.
I mean, we already know that, for example, dust needs to be included except from SIBA, you know, and it is a very complex thing to include. And there's other effects, there's other phenomena. Yeah. All right. I think we can conclude here.
Yeah, I think.
Thanks for playing along. Very interesting.
Thank you very much for participation.